Welcome. Today we're diving into the fascinating world of hash tables, a fundamental data structure in computer science. Hash tables are known for their incredible efficiency when it comes to storing and retrieving data. Imagine being able to find information almost instantly, no matter how much data you have. That's the magic of hash tables. In this video, we'll explore what hash tables are, how they work, and why they're so important in programming. We'll also look at real-world examples and common use cases, so whether you're a beginner or just brushing up on your knowledge, you're in the right place. Let's get started by understanding the basic concept of a hash table. Hashtable is a special data structure that allows you to store data in key-value pairs. Think of it like a giant filing cabinet where each file is labeled with a unique key. When you want to find a file, you don't have to search through every drawer. You just look up the key and you're there instantly. This is possible because hash tables use a process called hashing to quickly locate the data. Hash tables are widely used in programming because they make data retrieval extremely fast and efficient. Now let's break down how this process actually works. A hash table data is stored as key-value pairs. The key acts like a unique identifier while the value is the actual data you want to store. For example, if you're storing information about students, the key could be a student ID and the value could be the student's name. This pairing makes it easy to look up, add, or remove data quickly. The key is always unique, ensuring that each value is easily accessible. This simple yet powerful concept is what makes hash tables so efficient for managing large amounts of data. Heart of a hash table is the hash function. This function takes your key and transforms it into an index, which tells the hash table where to store or find the value. A good hash function spreads keys evenly across the table, minimizing the chances of two keys landing in the same spot. This process is what makes hash tables so fast. If the hash function is well designed, you can access any value in constant time, regardless of how much data you have. Next, let's see what happens when two keys end up at the same index. Sometimes two different keys can produce the same index in the hash table. This situation is called a collision. Collisions are a normal part of using hash tables, but they need to be handled carefully to maintain efficiency. There are several strategies to deal with collisions, which we'll discuss in the next scenes. The key takeaway is that collisions don't break the hash table, they just require a bit of extra work to keep everything running smoothly. Handle collisions. Hash tables use special techniques called collision resolution methods. The two most common methods are chaining and open addressing. Chaining involves storing multiple values at the same index using a linked list or another data structure. Open addressing, on the other hand, searches for the next available spot in the table. Each method has its pros and cons, and the choice depends on the specific needs of your application. Let's take a closer look at each method, starting with chaining. Chaining is a straightforward way to handle collisions in a hash table. When two keys hash to the same index, both values are stored in a list at that index. This means each slot in the hash table can hold multiple values. Chaining is easy to implement and works well when there are many collisions. However, if too many values end up in the same slot, it can slow down data retrieval. Still, for many applications, chaining is a reliable and effective solution. Open addressing is another popular way to resolve collisions. Instead of storing multiple values in one slot, open addressing searches for the next available slot in the table. When a collision occurs, the hash table checks the next slot and so on until it finds an empty one. This method keeps all data within the table itself without using extra data structures. Open addressing can be very efficient if the table isn't too full, but performance drops as the table fills. Now let's explore some common open addressing techniques. Linear probing is a simple open addressing technique. When a collision happens, the hash table checks the next slot in a straight line until it finds an empty one. This method is easy to implement and works well for small tables. However, if many collisions occur, it can lead to clustering where several values end up close together, slowing down retrieval. Despite this, linear probing remains a popular choice for many hash table implementations. Quadratic probing is another open addressing technique that helps reduce clustering. Instead of checking the next slot in a straight line, quadratic probing checks slots at increasing intervals. For example, it might check one slot away, then 4 slots away, then 9, and so on. This spreads out the data more evenly and reduces the chance of clustering. Quadratic probing is a bit more complex than linear probing, but it can improve performance in larger tables. Double hashing is a powerful open addressing method that uses a second hash function to determine the step size when searching for an empty slot. This approach helps distribute data even more evenly across the table and further reduces clustering. Double hashing is especially useful when you need to minimize collisions and maintain fast access times even as the table fills up. It's a bit more complex to implement, but the benefits often outweigh the extra effort. Hash tables support three main operations: insertion, deletion, and search. Insertion adds a new key-value pair, deletion removes a pair, and search finds the value for a given key. Thanks to the hash function, all these operations can be performed very quickly, often in constant time. This makes hash tables ideal for applications where speed is critical. Let's look at each operation in more detail, starting with insertion. You insert a new key-value pair into a hash table. The hash function calculates the index for the key. If the slot is empty, the pair is stored there. If there's a collision, the hash table uses its collision resolution method to find the right spot. This process is fast and efficient, allowing you to add new data without slowing down the system. Insertion is one of the key strengths of hash tables, making them a popular choice for dynamic data storage. Searching for a value in a hash table is incredibly fast. You provide the key and the hash function calculates the index where the value should be. If there's no collision, you find the value instantly. If there is a collision, the hash table uses its resolution method to locate the correct value. This speed is what makes hash tables so valuable in applications like databases and caches, where quick lookups are essential. Leading a key-value pair from a hash table is just as efficient as inserting or searching. The hash function finds the index for the key and the pair is removed. If there's a collision, the hash table uses its resolution method to ensure the correct pair is deleted. Deletion is important for keeping the hash table up to date and efficient, especially in applications where data changes frequently. Load factor is a key concept in hash tables. It measures how full the table is by dividing the number of stored elements by the total number of slots. A high load factor means the table is getting full, which can lead to more collisions and slower performance. To keep things running smoothly, hash tables often resize themselves when the load factor gets too high. This ensures that data retrieval remains fast and efficient. When a hash table becomes too full, it needs to resize to maintain performance. Resizing usually means creating a new, larger table and rehashing all the existing keys. This process can be time-consuming, but it only happens occasionally. Once the table is resized, operations return to their usual fast speed. Resizing is an important part of keeping hash tables efficient, especially as the amount of data grows. One of the biggest advantages of hash tables is their efficiency. Most operations like insertion, deletion, and search can be done in constant time, meaning the speed doesn't depend on how much data you have. This makes hash tables perfect for applications where speed is critical. However, efficiency depends on a good hash function and proper handling of collisions. With the right setup, hash tables can handle massive amounts of data with ease. Hash tables are used in a wide variety of applications. They're the backbone of dictionaries and maps in many programming languages, allowing for quick lookups and updates. Hash tables are also used in databases, caches, and even in networking for routing data. Their speed and flexibility make them a go-to choice whenever fast data access is needed. Let's look at some specific examples of where hash tables shine. Programming, dictionaries and maps are built on hash tables. They let you store and retrieve data using keys just like a real-world dictionary. For example, you can quickly find the definition of a word by looking up its key. This makes dictionaries and maps incredibly useful for tasks like counting word frequencies, storing user information, and managing settings in software applications. Hash tables play a crucial role in database indexing. Indexes help databases find records quickly without scanning every row. By using hash tables, databases can jump straight to the data they need, making queries much faster. This is especially important for large databases with millions of records. Efficient indexing is one reason why modern databases can handle so much data so quickly. Hashing is another area where hash tables excel. Caches store frequently used data so it can be accessed quickly. Hash tables make it easy to check if data is already in the cache and retrieve it instantly. This is vital for web browsers, servers, and many other systems that need to deliver information fast. By using hash tables, caches can keep performance high and response times low. Compilers use hash tables to manage symbol tables, which keep track of variables and functions in a program. When compiling code, the compiler needs to quickly look up information about each symbol. Hash tables make this process fast and efficient, helping compilers translate code into machine language without delays. This is just one more example of how hash tables power essential software tools. Networking hash tables are used for tasks like routing and managing connections. Routers use hash tables to quickly look up where to send data packets, ensuring information gets to the right place without delay. Hash tables also help manage sessions and connections in web servers, keeping everything organized and efficient. Their speed and reliability make them a key part of modern networking. Hash tables are often used to store passwords securely. Instead of saving the actual password, systems store a hashed version. When you log in, your password is hashed and compared to the stored value. This adds a layer of security, making it much harder for attackers to steal passwords. Hash tables make this process fast and efficient, helping keep your information safe. Building a hash table from scratch involves several key steps. First, you need to choose a good hash function that distributes keys evenly. Next, you decide how to handle collisions using methods like chaining or open addressing. Finally, you implement the main operations: insert, delete, and search. With these pieces in place, you have a fully functional hash table ready to manage data efficiently. Selecting the right hash function is crucial for a successful hash table. A good hash function spreads keys evenly across the table, minimizing collisions and keeping performance high. It should be fast to compute and work well with the types of keys you're using. Many programming languages offer built-in hash functions, but sometimes you'll need to design your own for special cases. No matter how good your hash function is, collisions are inevitable. The key is to handle them efficiently. Chaining is simple and works well for many cases, while open addressing can be more efficient if the table isn't too full. The choice depends on your data and how you plan to use the hash table. Testing different methods can help you find the best fit for your needs. Dynamic resizing is an important feature of modern hash tables. As more data is added, the table automatically grows to maintain performance. This involves creating a new, larger table and rehashing all the keys. While resizing can be time-consuming, it only happens occasionally. The result is a hash table that stays fast and efficient no matter how much data you add. While hash tables are powerful, they do have some limitations. They can't store duplicate keys, and performance can drop if the table gets too full or if the hash function isn't well designed. Hash tables also don't maintain any order among the data, which can be a drawback for some applications. Understanding these limitations helps you decide when a hash table is the right tool for the job. Sometimes, other data structures are a better fit than hash tables. For example, if you need to maintain order, a balanced tree like a binary search tree might be better. If you need to store duplicate keys, a multimap could be the answer. Understanding the strengths and weaknesses of different data structures helps you choose the best one for your needs. Hash tables aren't just theoretical, they're used in real-world systems every day. From managing user accounts on websites to speeding up searches in massive databases, hash tables make modern technology possible. Their speed and efficiency are the reason why so many applications rely on them behind the scenes. Next time you use a search bar or log into a website, there's a good chance a hash table is working for you. Python, the built-in dictionary type, is implemented using a hash table. This means you can store and retrieve data using keys with incredible speed. Python handles all the details for you, from hashing to collision resolution. This makes dictionaries one of the most powerful and easy-to-use features in the language, perfect for everything from simple scripts to complex applications. Java provides several hash table implementations, including HashMap and Hashtable. These classes let you store key-value pairs and offer fast access to data. Java's hash tables are thread-safe and come with features for handling collisions and resizing. This makes them a reliable choice for building robust, high-performance applications. C++, the unordered map container, provides a hash table implementation. It allows you to store key-value pairs and access them quickly using keys. C++ gives you control over the hash function and collision resolution, making it a flexible choice for performance-critical applications. With unordered map, you get the speed of hash tables with the power of C++. JavaScript uses objects and the map type to implement hash tables. These structures let you store data using keys and retrieve it quickly. JavaScript's hash tables are widely used in web development, powering everything from user interfaces to server-side applications. Their simplicity and speed make them a favorite among developers. Go or Golang has a built-in map type that uses a hash table under the hood. This makes it easy to store and retrieve data using keys with all the benefits of hash tables. Go's map type is optimized for performance and is a core part of the language, making it a great choice for building fast, scalable applications. Ruby uses the hash class to implement hash tables. This class lets you store key-value pairs and access them quickly. Ruby's hash tables are easy to use and come with features for handling collisions and resizing. They're a popular choice for building web applications and managing data efficiently. In PHP, associative arrays are implemented using hash tables. This allows you to store and retrieve data using keys, making PHP a powerful language for web development. PHP's hash tables are fast and flexible, supporting a wide range of applications from content management systems to e-commerce platforms. Zhash offers several hash table implementations, including Dictionary and Hashtable. These classes provide fast, key-based access to data and are widely used in net applications. Zhash hash tables are designed for performance and reliability, making them a solid choice for enterprise software and large-scale systems. Swift uses the dictionary type to implement hash tables. This type lets you store and retrieve values using unique keys with all the speed and efficiency of a hash table. Swift's dictionaries are easy to use and integrate seamlessly with the rest of the language, making them a great choice for iOS and macOS development. Kotlin provides the HashMap class for hash table functionality. This class allows you to store key-value pairs and access them quickly. Kotlin's hash tables are efficient and easy to use, making them a popular choice for Android development and other modern applications. Rust's standard library includes the HashMap type, which provides hash table functionality. Rust's hash tables are designed for safety and performance, making them ideal for systems programming. With HashMap, you get all the benefits of hash tables, plus the reliability and speed that Rust is known for. To get the most out of hash tables, follow some best practices. Choose a good hash function, handle collisions efficiently, and resize the table when needed. Avoid using hash tables for ordered data or when you need to store duplicate keys. By following these guidelines, you can ensure your hash tables remain fast, efficient, and reliable. Hash tables are one of the most important data structures in computer science. They offer fast, efficient storage and retrieval of data, making them essential for everything from programming languages to web applications. By understanding how hash tables work and following best practices, you can harness their power in your own projects. Thanks for joining us on this journey through hash tables. Keep exploring and happy coding.